Yeah, so just for everyone who just joined, this is Zach, who's an undergrad student at Loughborough. Has just finished his thesis, which was around integrating Monty, thousand brain system, into a robotic setup. And yeah, very cool project. Yeah, today's going to be talking about what he kind of built, and also the challenges along the way. As the first person doing this, I think it's yeah, impressive how far you managed to get.
Thanks.
Yeah, really looking forward to it. And then yeah, if you don't mind, we'll probably ask questions as we go.
Yeah,
But yeah, otherwise feel free to start.
perfect. I was going to say the meeting is about sorry, the presentation is about half an hour-ish. I wasn't able to get to an hour or 45 minutes, but feel free to stop me and ask questions on the way or ask questions at the end as well. I've got a slide for questions as well. So whatever you feel
Perfect.
like. Right. Let me hopefully get this off the ball and sharing. Wonderful. Okay, right, I'll start then. So thank you for the introduction. As I've already been introduced, I'm Zach. I'm a student at Loughborough University. My degree is robotics, mechatronics, and control engineering. If you like the long term of the degree, I just call it robotics. I've just finished, so I graduate actually in 2 days. I go back up to Loughborough to graduate. But this is my presentation on the undergraduate dissertation that I did. So yeah, without any further ado, I'll go ahead. A bit of background first. I first heard about the Thousand Brains theory in 2024, and I'm a massive audiobook fan, and I was looking for another book to listen to when I stumbled across A Thousand Brains. I was captivated by the idea, and so I decided to write a LinkedIn post about it. Vivian liked this post, and I reached out to connect and stay updated with the work of the Thousand Brains project. And then some months after that, the Thousand Brains project was open sourced. Now, if you let me go on a little tangent before I properly start, at the beginning of my degree, large language models, starting with the release of ChatGPT, became all the craze. These new tools were novel and really widely spread, and it might have been the first time that the term artificial intelligence had really fully reached the public consciousness, which is probably why LLMs have come to dominate the meaning of the term AI and still do today. In much of the media I've seen since the release of ChatGPT, the term AI typically only refers to LLMs when it's used. Despite all the media hype, I was convinced that LLMs were not the solution to intelligence. They were very good tools, but they didn't learn like us. They were more like very clever parrots. No person I've ever met has had to digest the entire contents of the internet in order to communicate. There is this obsession with scaling current LLMs, building bigger and bigger data centers when our brains appear to do the equivalent at a fraction of the cost. So when I came across the Thousand Brains theory, I was convinced the entire field might be heading in the wrong direction. And I decided I wanted to play a role in aiding the Thousand Brains project and the new framework you guys are all working on. So to help the Thousand Brains project, I decided to include Monty in my final year dissertation project. I'm not an expert in neuroscience or software engineering, so I didn't think I could provide much in terms of development, but I hope to create a project that might help to spread awareness and inspire other community members to get involved. I reached out to Vivian, who put me in touch with Niels to be my external supervisor, and I began to define my project. For my dissertation, I was required to create an aim and set of objectives. So the aim was, as you can see there, to expand upon a stress test the Thousand Brains project. I'm creating a sensorimotor system that enables learning and recognition of real-world objects in a human-like way. I broke that down into 4 objectives. The first being actually defining the requirements of the system by analysing what Monty could do at the time. Actually constructing the system, integrating Monty into that sensorimotor system, and then evaluating how the system performs. This is a project timeline. This screenshot's actually quite old. I didn't get a chance to update it, but this is a Gantt chart that I made of the whole project. You can see I captured this back in December, I think it was. It's sort of just high-level project steps going down. This is the way that I laid it out. It's probably not the best way, but I'll do it. This is a zoomed-in equivalent of just December and January and February there, and you can see what I intended to do. Those are all 100% now, so finished the project's Gantt chart that was. Just as a proof of concept, I decided to implement my own equivalent of the Monty Meets World experiment that you guys designed. I think you ran that during a hackathon, might have been a year or so back. I ended up using the back-facing LiDAR of an iPad instead of a front-facing camera, which was used in the original Monty Meets World experiment. So I'm showing you here that experiment, me holding the Mentor mug, Thousand Brains Project mug. I then processed the captures with a Python script that I took from the camera on the back of the iPad so that it could be accepted by the camera sensor module, the camera SM, which you guys designed as part of the original pipeline. So yeah, just a proof of concept, just to show that I could use Monty and get it working on an iPad. To help get some ideas for my design, I did some background research into a similar object recognition system. So this is my design for my Sensorimotor system. I looked at the well-known YOLO algorithm to the lesser-known neural fields and WISC-I robot, which are more adjacent. These two are more adjacent to the sensorimotor learning that is applicable to Thousand Brains Project and Monty. Neural fields combines a camera with tactile sensors, and it uses them as like super short range cameras with only depth inputs. These grippers move around a 3D object to learn and recognize it. It uses quite heavy deep learning architecture though. The WISC-I robot, on the other hand, is based on the rat's midbrain, and their project rejects the traditional deep learning approach in favor of sensorimotor learning. So very similar to Thousand Brains Project, but they took a different approach to it. Here you can see the simulated and real-life version of the WISC-I running over ROS, the robot operating system. I'll just pull up the laser pointer. Yeah, simulated, and there's the real life. So this is WISC-I. It's designed to explore and model its environment in the same way a rat does. So I think it has, I believe it has cameras, and it also has these whiskers, essentially, which are quite a cool design. To construct my sensorimotor system, I needed to select some sensor modalities, and I set out with the intention of picking 2 different sensors and having their learning modules vote across modalities to identify objects. But you'll see later on how that didn't exactly go to plan. Here you can see a range of different sensors and sensor fusion techniques for object recognition that I looked into. The 3 combinations on the right was my main focus. So Loughborough had already said that I could use their Z stereo camera there on the left, and the UFactory robot that they had already in-house. So I knew one of my sensors was going to be vision because I already had that high-spec equipment. Originally, I was set on visio-tactile fusion, so that's combining a camera with a tactile sensor. But after looking into it, I came to realize the difficulties introduced by tactile sensing were quite a lot. There are some really nifty sensors out there. I think Neil shared a few with me, but these were typically out of budget. For the tactile sensor to work, I needed to deal with object interaction as well. If the object being modeled isn't secure, it'll move when touched and throw off the readings. Overall, tactile seemed to introduce too many challenges for the time frame, and so I decided to go for vision and time of flight. So the plan was to mount the time of flight sensor to the end of a robot and have it move like a finger over an object, and then have the camera statically mounted like an eye in a socket scanning over an image of an object. And these were intentionally based around the existing surface and distant agents which Monty supports, and they both have the RGBD input. So you can see the intended flow of the sensorimotor system I had in mind in this diagram. You got the surface agent and the distant agent with the time of flight sensor and the stereo camera. I think this is actually based on one of the figures in one of your papers. So the keys are the same, and you can see the flow of information as it's converted by the sensor module into the cortical messaging protocol format. I didn't get a chance to perform the lateral voting, which I've got here across the learning modules. So that was potential extension to the project that I'll mention later on. And the goal states which come out of the learning module in order to direct the motor system, to the motor system, which the motor system converts into the robot movements or the saccades on the picture. This is the distant agent setup, and it extends the Monty Meets World pipeline to capture and index RGBD scenes. You can see the experiment flow for both experiments are very, very similar. And that was why the distant agent was perhaps the easiest to set up. It's designed to learn and recognize objects from a single RGBD viewpoint. And in order to meet the input requirements of the camera SM sensor module input, there were some utility functions I created for the Z camera so that the captures were converted into the correct format. Like the Monty Meets World pipeline you guys created, this setup involves a sensor patch which saccades on the image, and there is some filtering under the hood to remove the desk plane and the background that might be around the image in the real world capture. Here is the surface agent experiment flow, and I'll come back to this in a moment and break it down a bit more. The time of flight sensor I ended up picking after looking into a variation of them that were in the budget I had was this little Make Sense A010 time of flight, and it has 100 by 100 resolution, 8-bit precision, and was very budget friendly. I think it was about 40 quid. Though I discovered quite late that this sensor didn't actually really meet my requirements, and its limitations became the main blocker for the surface agent. You can also see there on the left is the CAD mount that I made to just mount the time of flight sensor to the robot. And the A010 time of flight comes with a GUI application for using the sensor, but I actually needed direct access. So I ended up creating an open source Python package for accessing the time of flight data directly. And that's accessible, I think, on my GitHub for anyone if they needed it for this sensor in the future. I then made an adapter so that Monty could use it. Because the surface agent needs to physically move the sensor, the experiment has to set up, it has more setup than the distant agent. So if we look back at the experiment pipeline I just introduced back there, I was able to reuse some of the same, I was able to use the same sensor module, as you can see in the other one, the camera SM, with the RGBD input by setting an empty RGB value and only focusing on the depth. But 3 new components had to be made in order to interface with the hardware, the time of flight sensor and the robot. So we've got the first one was the real world environment. This is responsible for converting Monty actions and goal poses into the robot poses, and then sending these poses to the robot. It also has a few safety features built in so that the robot won't accept any silly motion commands that sends it through the floor. That had to be added on at the end after the robot try to go through the floor. We've also got the real world environment interface. This passes on motor policy metadata at each step, such as absolute goal poses. We've got the real world surface policy. This is our motor policy based on the existing simulation. Oh, sorry, didn't mean to do that. There we go. Based on the existing simulation, but the simulation-based surface policy that you guys have already made, it's based on that, but adapted for physical sensing constraints of the hardware. So it has some semantic filtered depth for movement decisions, meaning it will only accept readings within a specified boundary, specified region. Any readings outside of this region, it won't be passed on to the sensor module, such as the background, things that are too far away to be seen, or that shouldn't be included in the actual reading of the object. It also adds a bit of a recovery system for when the object is lost from sight, so it'll start to move it. If the robot moves the sensor off of the object and it's looking at the surface of the table, that tabletop surface is filtered out so it can't see anything, and so it will try and move back to where it last saw information. At the experiment start, the environment, so this is just a run through the experiment. So at the start, the environment moves the robot to a specified home pose, and then begins to issue motor commands requested by the motor policy, ensuring the arm has converged and settled before accepting any new commands, so making sure it's settled. Then a burst capture of depth frames is collected, which is averaged to reduce the frame-to-frame jitter and turned into observations. Observations are then fed back to the next policy decision, and valid observations are added to our evidence. The 4 movement actions are these. I think this is defined in the Thousand Brains project docs, but adapted so that the move forward closes the gap to desired object distance, robot moving closer, orient horizontal, orient vertical, rotate the sensor about its surface normal axes in order to try and keep the sensor patch perpendicular to the object surface, and then move tangentially, then slice the sensor along the surface.
Just to check, I understood the burst capture. So, as in, because of like tiny movements in the robotic arm, even when it's sort of standing still, you take lots of images and average over. Is that right?
Yes, that's what the burst capture does. So I found that there was variations in what the time of flight sensor was capturing, because it's quite a budget sensor. And so what I would do to filter out a certain type of noise, I would capture 10 captures and then average those.
Yeah, okay.
And the parts of that capture that were valid were then passed on. So if it was within the semantic mask, it would
Right.
go, yeah, I'm happy with that. We can count it as evidence. This is a valid observation. Otherwise, it would reject it.
Yeah, thanks.
So I won't talk too much about the filtering, but there were some filtering techniques I applied to the time of flight data. As I mentioned, it was very noisy, and you'll see some of the results later, how noisy they were. So yeah, you got the Huber plane fitting, and some of the averaging, the filters that I applied. I think I already mentioned the semantic mask, which is just this mask applied in the world frame. That was probably the main one to remove the background and focus on the object. And this is all the surface agent still, the robot with the time of flight sensor attached to the end. Another thing required as part of the setup was defining the reference frames for each component, and making sure the coordinate systems worked out. The robot base frame and Monty world frame are in the same position, but in different orientations. So some reference frame transformations need to be done so that Monty and the robot can understand one another, understand each other. A tip for projects like this is to be very careful when determining these frames, and maybe even write a little Python script like I've shown here to double check them. Don't make the same mistake as me and spend a week debugging only to find out your coordinate frames are nonsensical.
Yeah, we've had our own share of headaches with coordinate frames in past projects too.
Yeah. I've drawn on the robot here. I think this is the Monty world frame. So yeah, you've suffered the same pain then. So the data set, this is the data set, not including the cardboard box that I was using for the surface agent. That was an additional thing to test how it recognizes flat geometries. You've got the wash bar, the tin, you've got the Star Wars mug, the Minecraft Fox, the cap, the Thousand Brains Project mug, and the hexagons. I chose a mix of glossy, matte, flat, and curved geometries, and I assumed that they would be non-moving, opaque, and reasonably rigid, so that they meet what Monty, the current limitations of Monty. So there'd be no modeling of object behaviors, for instance. Onto the experiments and results. So here you can see how, sorry, was that a question? No, okay. Here you can see how I've extended the Monty Meets World pipeline for the distant agent experiment to include captures from the Z stereo camera. At each episode, the user can choose to select a new image and say, well, they can select to capture a new image using the stereo camera, and then save that image to a new scene or a new version of an old scene. So you can see here, I've got a selection of existing ones that I captured. They're all captured in the same location as the Monty Meets World dataset, and they can be selected by this index. And these are some of the ones that I've just pulled out from here. So scene 1 is the Thousand Brains Project mug, and then scene 2 is I think probably the Star Wars mug, something like that.
So were you rotating the objects then, like during learning and kind of trying to fuse sort of learning of different faces together?
Yes. So I'll show you an experiment I ran in a sec where I just I only introduced sorry, I pre-trained on just the standard orientation of each object, so the one that faces the camera. And one of the experiments I ran was to see how well it could detect other orientations,
Yeah, okay.
having only
Right.
learnt the first orientation. There
Yeah.
are definitely some more experiments that I'd like to run in the future with the distant agent, because I don't think I covered all bases here.
Yeah, but no, I was just curious because yeah, it would be challenging to if you start rotating it, then it's kind of like, okay, well, how do you kind of capture the ground truth
Yeah,
rotation if you want to do a supervised experiment, at least to kind of fuse those faces?
yeah, keep it in the
And
exact same. Yeah,
right.
yeah. So it was a bit. I tried to keep them reasonably placed, but of course, yeah, you are moving them, so it's not perfect.
Yeah.
This is the demo of one of the distant agent experiments, and this is just the evaluation, I believe it is. Yeah, so follow it's the same as the Monty meets World pipeline, just with the Z camera attached to it. And I think what I'm doing here is yeah, I'm just going through each of the objects to show you in its first orientation facing you, how quickly does it detect it. And you can, it's already been pre-trained on this orientation. And I'll show you one more and then move on. This is T10. Yeah, and you can see how I'm selecting them here from the captures I've already taken. So these are some of the results in terms of the actual graphs from the distant agent with a single episode of training performed on each object. Monty correctly identified each of these objects when reintroduced the same item in the same position after pre-training, which is fair enough. I then did an experiment to see how Monty's recognition accuracy holds when objects are presented in orientations not seen during pre-training, as I mentioned before. As expected, because the pre-training graphs only had one view of the object, accuracy tends to collapse for orientations that don't look similar to the original orientation. So this is the one it was trained in, and then as you see, as it turns, it starts to lose it. These graphs show the accuracy and rotation error on each orientation averaged across all of the objects, and you will see 270 degrees is the worst one for all of them.
So yeah, how many objects were there? There were 5 total.
Sorry, say that again.
So how many objects total were in the data set?
There are 7 for the distant agent.
Okay.
So yeah, it's a bit of a crude graph, I have to say, to be fair. I've averaged them across that. What might be nice is to show you how each of them performed individually.
Yeah, I was gonna say, do you
Oh,
remember
that's
if
nice. It's
something
still
like
above chance.
yeah, right.
I
Yeah,
mean,
do you remember how the T10 performed, for example, like some of the objects with symmetry?
Oh, I don't remember, but I think because it was all the same, because it looks very similar all around, I think it struggled. Although the color variation does differ around the T10, so the front does look like it's different colors from the back.
Okay, yeah. I'd be curious if it still kind of recognized it just because of the kind of natural symmetry.
Yeah,
But yeah.
I think
Yeah,
a lot of sorry.
I was just gonna say, I mean, it's actually good that the accuracy drops here because it shows that it's not just looking at the color, for example, and saying, oh, this is the only orange object I know about, but it's actually saying, like, I mean, looking at this fox from the side, it has a very different shape than from what it has learned.
Yeah,
And so I think it makes sense that it would say, this is a different shape than what I've seen before.
yeah, I don't recognize it that well. It looks, yeah, because of
Yeah,
the different orientation, it looks almost completely different.
right.
I then did a continual learning experiment with the distance agent. So I picked 5 of the objects of the 7. I didn't pick the T10. I don't think I think I dropped another one. I can't remember what the other one is. And I reintroduced these 5 objects 3 times over 3 epochs. And I'll explain the results of this, why it's like this. The blue means that a new object graph has been successfully created. The red means that the object has been misidentified and is confused. And then the green means that the object has been successfully recalled and matched. I found that my setup always created new models of the first two objects presented to it, and then struggled to seed graphs for other new objects. So you can
So
see.
was this unsupervised as well? Sorry,
Yes.
to check. I see. Okay, yeah. So here was also testing whether it would recognize that this is an entirely novel object and create a new one.
Yes. Yeah.
Okay.
So I'd introduce the first epoch. I'd give it the 5 objects for the first time, having not seen anything before, and then I would see how well it performed with continual learning. And it worked well for the Thousand Brains Project mug and the Star Wars mug. You can see every time they were introduced in the next 2 epochs, they were then recognized and built upon. But because the hexagons, the fox, and the cap were not seeded as a new graph in the first epoch, they were misidentified. They kept being misidentified throughout. I suspect that my experiment configuration might be to blame for this, and that the config might have just been too lax for unsupervised seeding of new graphs. So perhaps some tweaking with my configuration might fix this, and it might not just create the first 2 model the first 2 objects and then struggle to make any more.
Yeah, the parameters for the unsupervised learning are a bit finicky, and it's one of the things on our roadmap to try and improve that a bit. And that's something that also our benchmark experiments struggle with, to make sure you create the correct amount of graphs when you first see the object, but then don't set the parameters too strict, so you don't create like 10 more new models every time you see the objects again.
Yeah, I did spend some time altering the configuration to see if I could get it to work, and sometimes it would go too far, and every time I introduced an object, it would create a new model, even if it was the same exact image. And sometimes it would go the other way, where it would go like, no, I'm only going to see the first one and nothing after that. Everything else is just this original graph. So I think my configuration, I think tweaking it might fix it, but as you say, there's a bit of difficulty. This is a demo of the surface agent. So you can see the motor policy moving over the actual Thousand Brains project mug and orienting to try and remain at the surface normal. But this wasn't perfect. I think this was the trickiest part of the project, the surface agent. The distant agent I didn't spend nearly as long on as the surface agent. And you'll see in the next slide. These are some of the results for the surface agent. And here you can really see the limitations of the time of flight sensor. The test I was doing here was just a simple modeling of either the wash bag or a flat cardboard box. Each time the surface agent is introduced to the object, it has no prior knowledge. Even though we aren't collecting many points here, the graphs are really erratic, and they don't really very well represent the object. You can see the path trace in blue, which is you can see the start and end, that it's just jumping from one side of the graph to the other. And my main suspect for these results is infrared scattering of the time of flight sensor. So I'll show you that now. So you can see I'm testing in quite a confined area, and what I suspect was going on was the infrared rays going down, and they're scattering and they're bouncing off the environment, causing some of the scattered rays to return to the sensor after a time delay, and this causes false readings. These phantom readings might still be within the predefined semantic mask boundary, and so they're accepted as legitimate values, even though they make little sense. And this is definitely more apparent when the sensor was at an angle and not perfectly perpendicular to the object, which was most of the time because it wasn't perfect. The sensor also quite struggled with the glossy surfaces. I think the scattering didn't help. The limitations of the sensor might have been my biggest challenge of the project. I attempted weeks of downstream filtering, and I mentioned the filtering a few slides back, but I attempted weeks of filtering in order to try and salvage the readings. But unfortunately, I think the physics just weren't on my side. One of the other challenges was I encountered was getting to grips with the low-level workings of Monty. I mentioned I'm not a seasoned software engineer. I have some experience, but there's a lot of information to take in and piece together. I have to say though, the documentation is fantastic. There's just a lot of it. I relied on Claude Code to help me with many of the code aspects of this project. It helped me to get my setup functional, but on the other hand, it may have hindered me as the code got quite complex at certain points. Finally, working on a changing code base was something it was sometimes a bit of a challenge. I tried to keep up to date with the latest Monty commit, and sometimes I found that I had to update my code as well to keep up with the improvements.
Yeah, I can imagine the changes we were making to the motor system in particular was kind of a bit of a double-edged sword, because on the one hand,
yeah,
now we can look back and say, okay, it's much simpler. But with all that happening during your project, yeah, I imagine that was a headache too.
Yeah.
To keep up
Well,
to
you
date
guys
with.
you were all improving it, so yeah, fair enough. I was like, is this commit going to break my code? And then
Right,
I'd go back and see, that's all changed, that's all moved now.
right.
But yeah, I think at one point, as you suggested, I cut off, and just I was like, okay, this is the final version. I won't update it anymore from here, and I'll collect the experiment data with this.
Right. Yeah.
Some tips for future community projects. So my first tip is to define your sensorimotor system early on. This must be something that follows or artificially creates the sensorimotor learning loop that Monty is founded on. Consider what Monty is currently capable of, as this might also be a blocker down the line. For instance, when I was designing my system, I didn't realize that the current infrastructure of Monty didn't support multiple independently moving agents. And that's things like that, definitely something to consider. Carefully pick your sensors. So downstream software filtering won't work. Sorry, it won't fix upstream sensor limitations. So make sure to pick a sensor that meets your needs. Consider what accuracy your sensorimotor system needs to be capable of, and adhere to that. I made the mistake of falling for what appeared to be a really brilliant budget time-of-flight sensor, but the time spent trying to filter and fix it was definitely not worth the savings. Before jumping straight into the toughest part of the project, start by building up to it. Don't try adding multi-agent complexity before you tested sensor modalities independently. First, get each of your individual sensorimotor systems working independently before trying to have them working together. The main point here is to build up in steps. Don't jump straight to the top. That makes things a lot simpler when you're actually coming to making a project. And finally, the discourse community is really friendly, and I found myself frequently asking questions, asking for advice and clarifications. Don't be afraid to reach out for help. I hinted at this in the discourse, some extensions to the project. But before I left Loughborough, I was working on scanning in some of the data set so that it could be used by the community, perhaps in the future. They're not perfect scans, but some are reasonably good.
They look pretty good, yeah.
Yeah.
Wow, those
They
look
look much better.
way better than ours.
Yeah.
So the difficulty with this scanner, you can see, is that it's on this turntable, and so the Fox came out really well. The bag came out reasonably well, but if you wait for the cup to turn, you can see the inside isn't perfect, because yeah, you can see a tiny bit of the inside, especially with the cap and the inside of the Star Wars mug and the Thousand Brains Project mug. It wasn't able to really capture the interior, so it was.
How is it getting the bottom of the mug?
Oh, so you can move it. So this bag up in the corner, I think it's like a gigabyte worth of 3D. I had to actually take it out the PowerPoint and take a screenshot of it because it was crashing the PowerPoint. Because you can take several scans and then merge them together. It's quite a nice 3D scanner. But yeah, these are all now released on my GitHub fork of the Thousand Brains project, the Monty GitHub. They're in the releases, and if anyone wants to download them. What I would do more. Sorry.
We'll have to get those, and at least replace the TBP mug scan with the one we
Yeah.
currently have, because we just used like the iPad camera and photogrammetry. I forget what
Oh
it's
yeah, like
called,
there's
but
also
yeah,
the
it
scanner
definitely
curves.
looks worse than this.
Well, the thing with that is these didn't have any color, so these are
Okay.
geometric, but they haven't got the color which you might have on the Thousand Brains project mug. So I don't know. I guess it could be used for geometric tests, but if you want to include color in the test, then you either have to add it in and things like that.
Do you
Yeah.
have the I don't know if you already tried this, but do you have the sort of inference data stored so that you can learn on like the digital models in simulation, and then see how Monty performs with kind of the actual real world data you collected? If that
As
makes
in like
sense.
with the STL, so with the actual file, sorry.
Yeah, so like put these in Habitat, and then Monty can easily kind of traverse the whole surface. I mean, like you say, there will be weird artifacts like on the inside of the mug.
Yeah.
But then, for example, when you showed the different objects at the 90-degree differences, it would be interesting to see, well, firstly, how the sim to real transfer is.
Mm.
And then because I think generally that's what we did for kind of Monty Meets World. Like we learned in simulation and then only did inference with the real world data. But yeah, I'm just curious if either you had a chance to try that, or if you have the kind of readings of the movement of the arms together with the depth readings, that you could kind of run that post hoc.
And see if it matches up. Yeah, okay.
Yeah.
I mean, yeah, this is definitely something that could be. I assume Habitat accepts STL files, or it might need to be converted into some other sort of file. But yes, definitely an idea to run this in simulation and build up these models.
Did it just, yeah, for example, like with the surface agent results you showed, like as you kind of said, like the samples were very sparse, so it doesn't seem sufficient to learn a model, but
Yeah,
maybe actually it would be sufficient to do the inference, and that it'd be, yeah, I don't know.
evaluate and determine which one it is
Yeah.
instead of learning it. Yeah, that's definitely a good idea. There's also I also have the collection. I showed you the index of all the distant agent captures. I have those, I think, uploaded somewhere. I think it's also on the same GitHub. And they're all the stereo camera captures from the Z camera. So they are in all the different orientations. Well, the 5 orientations that I was capturing. So could be tested with those as well.
Nice.
This is just a bit about what I would do with more time. So the first is I'd love to be able to implement this into LM voting within and between the agents. That was the original intention of the project, but I was sort of limited by my knowledge and the issue with the time of flight sensor. Carry out more tests with the distant agent setup. So as you mentioned, there may be scanning in from these STL scans. I could perhaps learn or pre-train on those and then identify it with the camera images. Replace the time of flight sensor with a higher resolution depth camera, and get that surface agent. If I still had access to it, get the actual surface agent with the robot functional, or more functional than it was, getting better data out really. And then introducing perhaps a tactile sensor. That was one of the original concept ideas. I do like the idea of a tactile sensor, and it was something that I think could work really well with Monty. Thank you. That's my presentation. This is my poster that I submitted as part of the dissertation. But if you have any questions, I'll try and answer the best I can. Thanks for listening.
Yay.
Nice. That was great.
That's really
Thanks.
great. Really great. I have a question for you, Zach.
Yeah.
So really nice and really ambitious project. So kudos to
Thank
you.
you.
And you talked about the tactile agents. Did you do any research on what sensors are available and how you'd go about that?
In terms of acquiring the sensors?
Yeah, just like what would you be, how would you have implemented that if you I just don't know. I have no knowledge of the tactile sensor world.
In
So,
terms of specifically the tactile sensor, sorry.
how do they work, and do people make them? Are there good choices out there?
I had some of the reading I did was about which ones are best for object recognition. And I read about how different people applied them in different ways. A lot of them applied machine learning techniques with like single sensors in order to recognize whole objects. But generally,
But
best.
are there people who make tactile sensors that specific for robotics that you can buy off the shelf? Is that stuff available?
There was someone actually on the discourse who sent me something halfway through the project to build your own tactile sensor. And I can't remember his name, but they actually constructed their own one. And I don't think it was perfect, but it was really quite cheap. You can literally build it from stuff off the shelf. So it was definitely something I considered as perhaps an extension if I had more time.
I mean, there's a lot of cameras, right?
Was it-
There's all kinds of cameras and distance
Yeah.
sensors and so on, LiDAR. So I just didn't know. I'm just curious. I have no idea what the world of tactile sensors look like.
Yes, they are they're less defined than other sensors. So cameras are perhaps the best one for this.
Yeah.
Yeah, and I think sometimes they even kind of build off of cameras. Like I think one of the more famous ones is Gel Sight,
Yes,
which kind of has like you can imagine like kind of a circle with some sort of gelatinous material or membrane, and then when you press it down onto a surface, it kind of disturbs, I guess, the surface, and then the camera, I think it's a camera-based thing, is basically reading out the kind of depth changes. Yeah,
Interesting.
but you know, when you think about like that, what's that? Sorry?
I think it is a camera. I think it's actually what these guys use. So there's a gel sight on each of these fingers, and they push down into the object, and there's a tiny camera inside that looks at how this bubble is being pushed down, and that's the tactile reading you get.
Interesting.
And I think part of that is maybe challenges around miniaturization. Like I think you could get like a really I think the depth reading you can get with a gel sight is like super high. Like if you put it on a coin, you would basically see the perfect penny face, like more high resolution than our own fingers, probably. But then, as opposed to I don't know whatever kind of kinetic kind of sensor, like to get it to have like thousands of sort of units within a few centimeters is probably quite challenging.
Cover the I just my ignorance here, but all these people building humanoid robots, and what do they have for tactile sensors?
Yeah, I'm also curious, but yeah, because what were you gonna say, Jose?
Oh, I guess I imagine tactile sensors to be like piezoelectric and not cameras. So I was a little bit surprised to say that the cameras were being used for tactile sensors. So are there off-the-shelf piezoelectric? I mean, there's probably a lot. I'm guessing.
There's a few different variations. There's
right.
I think probably the most well-known ones are the piezoelectric. They're some of the original ones. It also depends on what type of like force you're looking for. If you're looking for like shear force or
right,
like
vibrations or
optical.
And I'd be curious about the resolution of those. Like I wouldn't be surprised if that's capturing force, but just like over quite like a coarse area. Just as a single reading.
So where is that reading coming from? So I think it's definitely an interesting thing. That definitely a technology that is being developed in the future, and hopefully will get progressively better, but not very accurate as compared to say cameras or like time of flight sensors and LiDAR.
Well, but I agree with you. With robotics, you really need great tactile sensors. And not just on the tips of the fingers, and we have them everywhere in our body. You need to know when your arm is bumping up against something, and I just don't know the state of the art. So it sounds like it's still in development, not advanced yet.
Yeah, I think it's definitely it's not there yet, from what I read. But hopefully something interesting soon that might be able to be used in this project. I think gel sight is definitely something that is being built out, and that could be quite interesting to be used in a project like this.
Right.
How I'm curious, the safety feature you mentioned, What exactly was that? Was it basically just in sort of world coordinates? You just said don't move beyond this plane, or was it more sophisticated? Or
There was a few different parts. So it was don't move beyond this plane. If you've got sometimes Monty would send movements which were quite aggressive. So it was like move 30 centimeters this direction. And if it was too far, I would say no. I'd have something to cut it off and say no, don't do that. Update and just tell the motor policy that you didn't take that action, because some of them could be quite aggressive. And then there was also when it fell off of the object, it would sort of deck up a cache of 5 last times it saw the object, and it would move back to that and then perform another action. And if it keeps moving off, it would move back up this deck, hopefully remaining on the object. But because of the scattering of the time of flight sensor, that often didn't fully work. So the robot would see, it would go, oh, I had a valid thing over here, and I'll move over here, and the object is now out of sight. I move back over here. It was a bit chaotic.
And yeah, you mentioned yeah, Monty can't support multiple agents moving independently yet. But since you have one, the camera is actually not moving at all. Was that a blocker for you, or it was more like you couldn't connect them both because of time constraints?
It was more I couldn't connect them in the time constraints.
Okay, yeah.
I wanted to. I was looking into how to connect them and work out where the camera is in the world frame, the Monty world frame, and on the desk. I don't think you can see it in any of the. No, I don't think you can see it in any of the pictures. But there were some QR codes, and this Z camera is great because it has an IMU built in. It knows it can tell you its angle, and if I can look at that QR code, I should have been able to work out where it was relative to the QR code, and then hopefully I'll be able to work out where the QR code is relative to the Monty world frame, and then determine positions based on that. But didn't get that far in the project, I'm afraid. That would probably be
Yeah.
another extension.
Okay, yeah. And then when you showed the pictures from the Z camera, it looked like it was quite far away from the objects. Was that because of the optimal range for the depth value?
Yes, that was another. I think I'm a bit further. Yeah, here we go. So that was another issue with the sensor. So well, this is an issue with the Z camera. Its stereo vision works from 30 centimeters upwards. So it had to be at least 30 centimeters away. These are actually cropped. The original image is you can see the whole robot. You can see part of the PC screen next to it, the monitor next to it. So I made the sensor patch quite small. It does reduce the resolution, but because of the technology, I wasn't able to bring it closer. So if I had more budget, maybe a smaller, a close range depth camera that that I can bring within 30 centimeters. But I still think it was able to pick up data as it was.
Yeah. Yeah, I think it was more visible on one of the animations you showed that like the patch is like is quite small
Yes. Oh yeah,
on the
you can
image,
see.
but it looked like yeah, you still got good
Yeah, you
depth
can see
readings and got
such
a
a
decent
tiny
amount of
patch.
points on the object. Okay, yeah. Yeah, I think that's what I
Yeah, yeah. So it's this is as far away as this is as close as I can get it without the depth reading starting to go bad. Um, so it's not perfect. I also had an auto targeting of the object. So if the object's not dead center, it will find whichever depth item is closest to it. So this each time it will find the object in the center, and it filters out this plane, this desk plane here as well, so it isn't distracted by that.
cool.
for the results you were showing, the 100% with the sort of like 000 orientation,
Yeah.
was that like kind of at a pixel level the exact same image, or with a different policy, or was it kind of the same rough position recaptured with the camera in a different setting?
So I think it was the same. I think I believe it was the exact same. Either that I captured, I think it was the same, but either that I would have captured the same image again without moving the object. So
yeah. So with light scattering and stuff may have been slightly different.
Would be interesting to see, I guess, almost similar in in the same orientation.
Yeah, because I mean, at least from the result from the 90-degree rotation, it seems like it might still be able to get close to 100% accuracy.
Yeah.
But it's that's always just something to be aware of, is especially if Monty's following the same policy, then it can be kind of really good results.
Well, it's still done very well considering it's only ever seen this angle.
Right.
So
yeah,
it's
that's what
going
makes
up
me think that it probably would get close to 100%.
Yeah, it's done considerably well. I think 270 degrees, which is orientation 3, is clearly, perhaps for some of them, it cannot make it out. It looks too different.
Yeah, I wonder if wondering maybe like the mugs orientation 270 had like the handle face on or something like that. If that was kind of what, because 90 degrees and 270 degrees should be kind of the same for some of the objects, but I guess for some of them there wasn't.
That should be better. The T10 should be matched.
Yeah.
Yeah, I can probably get the if you'd like, I could see if I can get each independent graph for each of the objects. Because as I say, this is a bit of a crude one where I've averaged them all together.
Yeah, I mean, if you've got a chance, it could be kind of interesting, and yeah, with the images, because I would be curious, kind of what is it about the 270 that's breaking for some of them.
Yeah.
Any other
I think
questions?
the random would be the worst, to be fair. It does.
And what was that exactly? Was that you just picking a random orientation?
Yes. So
Okay.
it was whatever I could balance without it
right
making shape. So I think the mugs are on their side, the T10's on its side, the hat's upside down. But yeah, and it still manages to get a reasonable score.
For the Fox example here, I would expect the random one to do the best because you can still see all the original features from the image it has learned on. But yeah, for some of the other objects, I guess if you're like flipping
it pulls it,
stuff like
it pulls the average down, I suspect.
Yeah.
Yeah, again, that would be kind of interesting to see how it does on that Fox, on the Fox random.
Yeah.
Versus the other ones.
Yeah, and then you mentioned the rotation error of the T10 because it seems to be the same all the way around essentially.
Right. But yeah, it sounded like for the this camera, it did have color information. It was just the time of flight that was depth only.
Yeah, time of flight had I think it was just black RGB. So yeah, I set 000, so it got nothing. And that's how I reuse the camera sensor module.
Yeah, okay. Yeah, any last questions for Zach or comments?
No, thanks again, Zach.
No worries.
Yeah.
Thank you very much.
Yeah, thanks so much
to meet you all.
Yeah, very nice to meet you, and yeah, we can touch base and follow up some of the stuff.
Yeah.
Great.
I look forward to seeing all the updates. I always keep up to date with what you guys are up to.
Nice.
Well, yeah, keep
us
updated with what you'll be up to.
Yeah.
Once you decide.
Right.
Bye.
All right.
Thank you very much, guys. Bye.
Take care, Zach.
Thanks.